Okay, we've looked at different terms and defined them in terms of AC power. We looked at real power and also reactive power, apparent power, and we looked at complex power. So what we want to do now is look and see why some of these terms exist, why they were defined in the first place. So what we're going to ask here is, since only average power is dissipated, in other words, that's the only thing that a resistor will do. It will dissipate P. Then why do we care about Q, for example? After all, Q just tells us that energy is absorbed and released by a reactive component, an inductor or a capacitor. So why do we care about that? Why do we care about apparent power? Why do we care about power factor? All of these came out of our analysis of the complex power equation. Why do those matter to us? Why does the power company keep track of those numbers? Well, let's look at an example to illustrate why all of this is important. Why more than just P matters, more than just the average power matters. And we'll start by looking at a very simple problem where we're going to assume we have an electric motor connected to the AC power mains. So Nashville Electric is supplying power to run a large motor for a factory you own, for example. And I'm going to use a fairly simple model to illustrate how that motor works. I'm going to model an electric motor as an inductor in series with a resistor. So in this case, for this electric motor, I first have an inductance of J.2 ohms, and the impedance of an inductance of J.2 ohms, and this inductance represents the windings of the motor. A motor, being an electromechanical device, is going to have coils in it, windings. And this represents that. So this is the impedance of our inductor. And I've also got a 0.1 ohm resistor, and this is going to represent the winding resistance, since I'm going to assume the wires are not made out of superconductors. Plus, in a motor, we're going to take some of that electrical energy and convert it into mechanical energy, and it's going to be dissipated in mechanical form. And so I want this resistance to also model that dissipation or that use of mechanical energy. So this is a resistance to represent electrical energy that's converted to mechanical work. All right, so this is my simple motor model, and we're connecting it into the power company here. So Nashville Electric is going to supply us with 120 volts RMS, and I'm going to assume this is at a phase angle of 0 degrees. And notice VRMS, I'm representing this as an RMS phasor. Okay. Let's first go through and let's calculate what is the complex power of that motor. That's easy enough to do. So in this case, I'm going to have a current I, phasor current I, flowing into that motor. I can easily calculate that. I is going to be equal to VAC divided by the impedance of the motor. VAC in rectangular form is just going to be equal to 120 volts RMS, just the magnitude. So that's 120 divided by 0.1 plus J 0.2, and I put that in my calculator, and what I will get is this is equal to 240 minus J 480 amps RMS. And now I can take this. I know that the voltage across the motor is, of course, just equal to VAC. It's connected directly across the motor. And so therefore, the complex power of the motor is going to be equal to VAC times I complex conjugate. And if I take the complex conjugate, then I'm going to get 120 times 240 plus J 480, which will be equal to 28.8 times 10 to the third plus J times 57.6 times 10 to the third volt amperes, which is equal to P plus JQ. So therefore, the motor has a power of 28.8 kilowatts. That's the power that's being dissipated by the motor. It has a reactive power of 57.6 kilovars due to the inductor. And notice I've got an inductor with a positive impedance and also positive vars, which is what I would expect. Now I can take this and convert S motor into polar form, and then what I'm going to get is it's equal to 64.4 times 10 to the third at a phase angle of 63.43 degrees volt amperes, and therefore the apparent power of the motor is equal to 64.4 kVA, pardon me, 64.4. And the power factor will be equal to the cosine of 63.43. And that will be equal to 0.4473. And because this is an inductor with a positive vars, this is going to be lagging. And so here we have all the numbers: real power, reactive power, apparent power, and power factor. Okay, so I've calculated all the numbers. The power company has these numbers. Then I get my bill. So I've been running this motor, and I get my monthly bill from Nashville Electric. And Nashville Electric, they send me a bill that I'm not happy with, because it turns out they're billing me for more than just the cost of the power, of the average power. So here's my claim. I'm only really using P, 28.8 kilowatts. That's the only thing I'm actually dissipating. That's all I should pay for. So that's my claim. I'm only dissipating the average power, the real power. And that's what I should pay for. Now, what about the reactive power in that inductor? Well, what does it represent? Every half cycle, the inductor charges, and then the next half cycle, it discharges. So energy flows into the inductor charges up, and I'm in effect borrowing that money from the grid, or pardon me, borrowing that energy from the grid, and then I turn around in the next half cycle, I put the energy back onto the grid. So I'm basically borrowing the power for half a cycle, but the next half cycle I give it right back. From my point of view, why should I pay for that? I'm not really using that power. Well, NES, Nashville Electric, has a different point of view. They say that even though I'm only borrowing Q, when I ask for them to borrow that, they must be able to supply it. So, even though Q is returned to the grid every half cycle, NES says we still have to give you that energy when you ask for it. Our generators must be able to supply it. So even though Q is returned to the grid every half cycle, the inductor absorbs it and then puts it back into the grid. Whenever you ask for it, they need to be able to supply it. They need to have that on hand, that energy on hand to loan to you. So just as when you borrow money from a bank, they have to be able to have money on hand to loan to you, even if you pay it back to them immediately. Which means that their generators have to be bigger, which means that that costs money, which means they're going to charge you for it. In fact, NES will tell you this. Our generators must supply, as it turns out, apparent power. Generators have to be rated for the apparent power. So this is NES's point of view. You are borrowing power, you're borrowing energy and then giving it back to them. But every half cycle, you repeat that. You borrow it for half a cycle, give it back the next half cycle. Point is they have to supply that energy. It costs them money to have generators large enough, and therefore there's going to be a surcharge. So here is the power company's point of view. You are therefore going to be billed for excess reactive power. You're going to be billed for having a large value of Q. Or another way to look at it, or having a low power factor. Our power factor is only 0.4473. If we had a perfectly resistive load, an ideal load with no reactance, we'd have a power factor of unity. And from NES's point of view, you need to increase that power factor. Your power factor is too low. You have too much Q. So you've got to fix that. Well, you can deal with this in a couple of ways. First of all, is you can pay NES for having low power factor and keep paying that surcharge every month. Or you could take a different tack. We need to somehow increase the power factor. How do you increase the power factor? We need something called power factor correction. So next time we will look at this example and we'll see how do we apply the principle of power factor correction and how does it work? How do we get around this problem of having to pay for the Q of that inductor? We'll look at that next time.